Good evening, sir.
Good evening. How are you doing?
Hi, sir. Shall we start the session, sir?
Sure.
Yes, sir. Good evening to all. I welcome Arun Iyer, sir, for the today's session. I welcome you, sir.
Thank you.
And also I welcome all the participants for the today's session. And also I welcome our HOD, Dr. Praveen Jay, sir. Welcome you, sir. And one information to all the participants, we will send the feedback and attendance link to the chat box only in the middle of the session. Please, only FDP register participants are informed to submit the form. Other participants don't submit the attendance form. With this, I request Arun Iyer, sir, to continue the session, sir.
Sure. Thank you. So I may have some network issues. Is my voice clear?
Yes, sir. You're audible, sir.
Okay. So there's no break in the network, right? Because I can just keep my hotspot on. Okay. I'll start sharing my screen. Let me know when you can see.
Yes, sir. You can tell us.
Okay. I have started to share. Let me know when you can see it.
Yes, sir. It's visible, sir.
Okay. So now I put it in presentation mode. All visible? All clear at your end?
Yes, sir.
Yes. Okay. Thanks. So continuing from yesterday, where we discussed some of the high-level aspects of VLSI design, we specifically talked about some of the motivations, how the field has come up, what sort of improvements have happened over the last so many years, how the scale and the integration aspects of VLSI has significantly picked up over the last 20 to 30 years. I touched upon very briefly, not in detail, aspects of Moore's law, and why. I mean that how that allowed the significant growth of the way we could integrate more and more functionalities on a piece of silicon, right? And also we compared two specific sets of design flows. One was ASIC design flow, other was FPGA based flows. And we also compared when FPGAs are historically, like the reason why FPGAs have been used by designers versus when people have gone for ASICs for designing their products. And then we looked at some specifics as to when and how some of those choices are to be made, and so on, right? Now, today, what we're going to do is we will start getting into some lower level details of some of the digital design aspects, specifically logic gates and sequential elements. These are very important pieces of combinatorial design and sequential design. So what we'll do is in this specific, there are like good number of topics which I plan to cover. And what I've done is, since we may not be able to cover all of them in one day, I spread this up over 2 days, and we will go over specifics and details of some of these topics here. And so there'll be a break at 7:45. So it's 7:03 now. So we break another 45 minutes nearly, and then maybe use the 15 minutes for any questions that you may have. Any questions from yesterday? Any general questions? Any points of views which we can do. So I will not break the flow when I'm presenting, so that I can complete the content in time. So I will take a break at 7:45, and then after that, after 15 minutes of Q&A, we will resume, and from 8 until 8:45 we'll resume, and then we will use the next the last break, the break number 2, from 8:45 to 9, to have another round of Q&A for the topic that was presented in that period, and maybe even any other item that you may have in mind, right? That's the agenda for today. And just to quickly see what we plan for tomorrow, we're going to cover the concepts of sequential logic. What are the major sequential elements? Some of the understanding the timing aspects of the sequential elements. What are the important care about? Let's say if you want to design some of these sequential elements like flip-flops and latches, how do you optimize for timing, for power or area, clock power, and so on. And then we're going to talk about characterization of standard cells, and then generation of timing libraries, which is very important for ASIC and SoC-based design flows. We're going to talk about that. I'm going to give maybe some simple examples of how a timing library may look like. And then I'll try to cover a couple of papers which talk about flip-flop design and how do I compared, how they are characterized. And then another paper for looking at how to optimize power or energy for some of these elements. Very high level, but we're going to spend some time. I will give the references so that you can read at your end and we can discuss on the last day. Okay, so let's quickly start. So the most important piece, or the which is used for digital logic, is basically a logic gate. So digital logic, obviously, as the name digital implies, is based on discrete discrete logic levels. So logic levels obviously are binary, which means we only have two levels, which means high or low, true or false, 0, 1, as we say, right? Now, logic gates are nothing but a symbolic representation of these clearly defined logical operations or logical functions. So what are the major logical operations or functions that we are aware of, or will focus on? Inversion, or which is, I think, in common language is also called the NOT. Union, which is also called as the OR. Intersection, which is also called as and exclusion, which is also called as excuse me, called as XOR. Right now, what's interesting is, I mean, obviously we know what NOT, OR, and XOR are because a lot of you have covered this in your digital logic in your early years, second year or third year. But what's interesting are these terms used here: inversion, union, or inversion also called complement, inversion, union, intersection, or exclusion. Now, these terminologies seem to be related to math and specifically the set theory aspects of math. And what's interesting is, when digital logic or Boolean logic was initially being developed, people actually realized that it's very closely related to set theory. And so when you and mathematically, people who study Boolean logic, or when the initial research and explorations were done 100 years back, people were looking at set theory and then trying to look at how the Boolean rules and laws apply, and then they were compatible. So that's why a lot of these terms are actually are sort of interchangeable. Intersection, which means, and obviously you know that it means that the inputs or the condition that you are taking together as inputs need to be simultaneously be true, right? So if my bus arrives and if it's a Volvo, I'm going to take it, right? Or if my bus arrives and it is before 9:15, I'm going to take it, right? So we use this, obviously, a lot of these logical aspects we use this in common language without even thinking about it, right? But there's a lot of detailed theory and mathematical aspects involved here to make it very formal. Once we formalize a lot of these concepts, that's when it becomes an engineering and a technology. Without putting all these concepts in a very sound mathematical foundation, engineering and technology never really develops from it. Otherwise, it just remains an art, right? So a lot of research have happened. Boolean logic is now is on a solid mathematical foundation, and because of which people have been able to build upon it and able to take it and build a lot of engineering and technological improvements and advancements have happened using that solid mathematical foundation. Especially in the 1930s, Claude Shannon, who was the first person who actually was able to relate Boolean logic to switching circuits, and actually was able to build the first set of logic gates and logic elements where he was able to relate switching circuits and Boolean logic together. Till that time, people were understood that you could build logic using switching circuits, but no one understood how to do it in a very structured form, like the way we do it. For example, we could draw truth tables. We know how to put gates together. We know that a plus a bar is equal to 0 and things of that sort, right? So Shannon was the first person who actually showed that you could think of it very systematically and formally. And once it was done, the whole field in terms of digital logic took off. So continuing with it, logic gates. Now, obviously, this is something which most of you are aware of. Not is nothing but it is true when the input is false, which means it is just trying to invert or do opposite of what the input is trying to say, right? And means when all the inputs or all the conditions are simultaneously true. If any one of them is not true, the condition will not realize, or the gate will not realize an output, which means nothing will happen, right? It will be logic 0. Or means any one of the inputs is true, right? For example, as we commonly use, right? In any day-to-day sort of usage, we use or. Sometimes what happens in our common language, sometimes we make a mistake of using and for or and or for and, right? And which is quite common because we don't really think about it very formally. But when you're actually trying to implement logic through gates, you have to be very clear about what logic or condition you're trying to test. And if some of you who actually do coding, like Python or C++ or any other language, you would have seen that a lot of these control statements that we have are basically the if-else statements. You have to write very clear and precise conditions for the condition to be evaluated correctly. Otherwise, you could be in the infinite loop, or it may not actually execute properly. You may not even get that control statement getting executed. So you have to be very precise and very clear about what is the logic condition that you want to test, right? If it's an OR, which means you expect any one of the inputs to be true for output to be true, and means all of them have to be true, and so on. XOR is something which is mutually exclusive, which means that in reality, if you look at it, it's basically counting the number of inputs that are true. It's basically looking at if it's an odd number of inputs which are true, then the output comes out to be true, right? And then you obviously can create equivalent versions of inverted versions of this. If I put a inversion at the end, at the output of AND, it becomes an AND. This becomes a NOR, and the XOR becomes an XNOR, which is nothing but a complementary behavior, which means and all inputs are true. In the case of the inverted version of an AND, which is NAND, it becomes a false. If any input is true, a NOR will be nothing but false, right? And so on. So most of you are obviously aware of it. We can just quickly skip it. Now, these are the symbolic representations of these gates. I think I assume most of you are aware. So these are truth tables, which are nothing but when you provide the input conditions, and since both the inputs are assumed to be Boolean, which means they can only have two states, 0 or 1, which means if you're going to have n number of inputs, in this case, n is equal to 2. So you're going to have 2 power n number of possible states or combinations to test the output for, right? So since there are two inputs, both input zeros, one of them 1, other one 1, both ones. And then if you're going to have 3 inputs, which means this whole thing doubles, right? So it becomes 8. And so you're going to have an appropriate number of outputs and so on, right? So a truth table is nothing but sort of a column or a row-wise representation of what the state of the inputs leads to then an output. It's sort of a good way to understand formally like how the gate actually behaves. So it is sort of putting the whole things that we described in words here into a formal structure here, right? Now, there are NAND gates, NOR gates. I'll just skip this. I think most of you are probably aware of this. Now, we can obviously build not just 2 input gates, but 3 input gates as well, which means, as I said earlier, since you have 2 power n number of combinations which can be formed on the inputs. So if there are 3 inputs, n is equal to 3. So 2 power n is Okay, so if there are three inputs, as I was saying, you're going to have 8 possible states that you need to check, or combinations that you need to check. Now, can you try at your end how the truth table of a NOR would look like? Can you just fill this table at your end, even though the answer is given here? Try at your end. I think most of you should be able to do it. Let's quickly take a half a minute to do this quickly at your end. Try this out. And then okay, and then similarly, some of you can give a try of how the AND4 will look like, how the truth table of AND4. So AND4, maybe you can try in the break if you don't want to do it now. So AND4 is expected to have 2 power 4 combinations of inputs. So someone seems to be scribbling here. Please avoid it. So 2 power 4 inputs, and so which means we're going to have 2 power states, which means 16 possible values, combinations which are going to be there in the truth table, and you can give a try for the AND gate. So what's expected obviously for an AND gate is we know that all inputs have to be 1, which means for the 15 set of 15 states, where any one of the inputs is 0, you're going to have a 0, and then the last one where all of them are 1, obviously is going to be 1. Right? Give a try for the XOR as well, the 3 input XOR. We can discuss that during the break. Okay, so this is fairly simple. I think most of you should be able to get this. Let's try to understand. So these are obviously just symbolic representations, right? These are just symbols. They don't mean anything because these are all on a paper, just theory, and it's just mathematical at this point. Now, how do we actually use this to build systems or a design which can be physically be realized? Now, which means we have to convert these physical gates into logic gates into some physical representation or implementation of these gates, right? So how do we do that? So these are some good summaries of how we go about it. Logic gate are built using switches. So that's basically been the approach that people have used for the last nearly 100 years. So logic gates are built using switches. We use switches. What type of switches? The switches could be mechanical. The switches could be electrical. The switches could be biological, could be anything, but it has to be switch. Switch means something which allows some state to flow through and or the state to be blocked. That's all it is. A diode is a switch, a form of a switch. A transistor is a form of a switch. A mechanical switch, for example, a door is actually a switch in a sense, right? And relays, electrical relays are switches. And then a clip is a form of a switch. So you can implement switches in any different ways. It doesn't need to be electrical, it could be mechanical. Obviously, electrical representation of switches are what we're going to talk about because we are talking about electronics here. But the concept of Boolean and binary logic or digital logic has got nothing to do with only electronics. It applies everywhere, and wherever you can build some sort of a switching type of a scheme, you can use Boolean logic there. Then turning on and off of the switches, as I said, in the case of an electrical system, controls the flow of current and voltages, which can be used to implement some logic, right? This is what we're going to talk about. Most importantly, in the last 70 years, since the transistor has been invented, so early transistors were bipolar transistor, BJTs. Then for the last nearly 50 years, it's been MOSFETs. So most of the logic gates are built using transistors, and specifically, we're going to talk about just MOSFET-based switches, right? And in specifically there, in terms of MOSFET, we're going to talk about CMOS-based logic gates, right? So, and I think some of you may remember your transistor basics. So transistor have 3 modes of operation: low resistance, off, which is also called as a cutoff, and then a current source / amplifier state. So Boolean logic just requires two states, on state and an off state. So even though transistor has three states, the current source or the amplifier state is generally not used. And we primarily operate in the low resistance state. That means the switch is completely conducting, and an off state, which means switch is blocking current. That's primarily the two states we care about. But when you're going from a low resistance to the off state, or from the off state to the low resistance state, we're going to transition or move through this state into the other state. In the case of analog circuits, the major source or major operating mode is going to be the current source or the amplified state, where we get a lot of linear behavior or very sort of proportional behavior of currents and voltages. And that's something which digital logic does not use or doesn't care about. For logic gates, I think I talked about this, and then I talked about this as well. So MOSFETs are the focus in this thing. So some of you may remember how a MOSFET will look like. This is an NMOS transistor. It's an NMOS transistor. So what do we have? This is a very simple view of it. We have a P substrate, right? A piece of silicon, P-type, on which source and drain are implemented. These are of N-type. And then we introduce between the source and drain an oxide on top of the substrate, P substrate. And we have a contact for each, because obviously we need to connect them to electrical signals or power. So there's some metal added here. Source connection is called. Another metal added here, source connection drain. Then on the gate, because it's oxide, it's not conducting, but we still need to be able to provide some voltage to it or current to it, which means we should be able to, we need to be able to provide a uniform voltage here, which means some piece of metal is added here. And then that connection or electrode is called the gate. So source, gate, drain. Now the substrate, because it's also electrically active, it's called the body. And then you can connect it to any way you want, ground or to the supply voltage or so on, right? Now normally what's done is, so this is an NMOS transistor, which means by default, if you just implement this device, it does not conduct any current, because it is a switch and it needs power. For any case, for any type of electrical circuit, without power, current will not flow, right? Which we need to apply some voltage, and there has to be a potential difference. A transistor is basically nothing but a controlled switch. Why is it a controlled switch? Because this path from source to drain or drain to source is resistive only if the gate allows it to be resistive. And for gate to allow it to be resistive, gate needs to be provided some potential. What potential depends on the type of the transistor. If it's an N type of transistor, it needs to be provided some high potential with respect to the source. And when you do that, automatically there's a lot of carriers or charges develop here. And then you have a conductive path from drain to source. And then when you apply a potential difference between source and drain, since now you have power, they're going to be charged. Electric field will be there, which means current is going to flow. Now, this basically is what a controlled switching operation is, which is what transistors basically are. Transistor is a controlled switch. It's a three-terminal device. If it's a two-terminal device, it's a resistor, right? A two-terminal device is a resistor, and even though it can conduct in both sides, but it is of no use to us because on its own, it doesn't have intelligence. It doesn't know how to control. Therefore, transistor was important to be invented, or any three-terminal device is very interesting and useful for building logic, because the third terminal allows us to control when and how the conducting operation is to happen. A resistor that way is sort of a dumb device. It's not an active device, right? Now, in this diagram, it's not shown that you obviously will be connecting a potential here. There will be some supply voltage, and there should be a potential difference between source and the drain. So if this is supply and the negative of the supply is grounded, Then this side is also grounded, which means there's a potential difference. Let's say the supply is VDD between drain and source. And then in this specific type of transistor, the N type, you need to raise the gate with respect to the source beyond a specific voltage. And once you plug that, let's say it's VDD, so the voltage is raised, this channel is formed. And since there's a potential difference between drain and source, the electric field will drive the charge carriers and current is going to flow. That basically is a transistor operation. I'm not getting into too much of details about the temperature, the inversions and subthreshold and those specifics. We're going to talk about that later briefly. But here, since we're primarily talking about digital logic and logic gates, that internal details of transistor operation is irrelevant, because what matters to is that there is a reliable transistor operation and we know how it works and what voltages to be applied. And as long as we know that, we can build logic out of it, right? So now, if it's an NMOS transistor, there's another type of transistor, which is a PMOS, where everything is sort of inverted. The P portions here become N. Sorry, the N portions here become P, and the P substrate becomes an N substrate. And then automatically, what happens is the behavior of that is complementary to this. And in that case, the source needs to have a higher voltage than the gate, and the current flows from the source to the drain, and which means higher potential has to be on the source, lower potential has to be on the drain. So from a digital logic point of view, what we do is we can abstract or simplify, have a simple view of a transistor, which is shown as this 3-terminal device. So there's an NMOS and there's a PMOS. So NMOS and PMOS have basically similar symbols, but there's one small difference. There's a bubble here, and the bubble obviously indicates that the logic polarity or the logic condition for this gate to have for this to conduct is going to be opposite to this, which means if this works with logic high and it's conducting, this works with logic 0 and conducts, right? So if you notice, it's shown here. So there is when the gate is low, what's going to happen? This is going to be an open circuit. It does not conduct, it's in cutoff. This will be like a resistive or a very low resistance path. When the gate is 1, this is going to be on, this is going to be off. See, there's a sort of complementary behavior here. Okay, so now continuing with it. So the logic gates, as I was said earlier, we're going to use switches and basically MOSFET-based switches for building the logic. Now, specifically, what's done is there's a special type of logic gates that are called CMOS logic gates, which basically is the state of the art. When I say state of the art, it means that is what the best implementations use in the industry and even in the academia. So there were other approaches which were prevalent in the 70s, where it was not complementary, which means PMOS and NMOS both were not used. But since the mid 80s, it's all been CMOS-based logic gates. And what exactly is CMOS-based logic gate? A CMOS-based logic gate is nothing but where the pull-up or the logic high flows through the PMOS, and the pull-down or the logic low is controlled by the NMOS. Now, as we saw here, because the PMOS and NMOS don't turn on together for the same input condition, and I think the important thing is the input is the same coming to the transistors here. The same inputs are going to both the transistors. And as you saw here, since for the same input levels, they don't turn on and off together, only one of them is, which means it's like a very safe circuit because there is no short circuit path from supply to the ground. And one of the networks, the pull-up network or the pull-down network, is the only one which is on, which means if PMOS is on, this will be off and blocks the path, and the path is only from the supply to the output. And if NMOS is on, this is off, the path is only from ground to output. And it's like a very reliable circuitry and very simple to design. And I think most of you would have also studied this in your colleges and as part of your curriculum. So hopefully this is not very difficult to understand. And you can obviously build this using, you can build any type of gates here. So if it's an inverter, what's going to happen is that you just need one PMOS here and one NMOS here, right? And so if you're building the same concept and apply it to start putting in more inputs here, let's say there are two inputs A and B, and we write this truth table, and the output is like this, I think you should be able to guess what type of gate this is. This is actually implemented using they're describing how the transistors are functioning here. So this should be fairly easy to explain or describe which type of gate this is trying to implement. Can just some of you type in the chat, which type of gate is this?
NAND.
Right, so that's an AND gate. That's good, and I think that's fairly easy to understand. So that's basically a NAND gate, and we need two inputs for it. And how? So what? This is just showing a black box. Someone has given you a black box. A black box means you don't know what the internals are, and they're saying that I provide this input, I see this output, and you know that quickly that this is an AND gate. But what will be important to know is, okay, it's an AND gate, but how do we build it using these transistors? I know that there needs to be a pull-up network, there needs to be a pull-down network. How do I hook them up? How do I connect them to make this, right? A lot of you would all obviously know this. Now, these are some other ways. So you have to connect some of the transistors in series, some of them in parallel. So series means the source and the drain flow from one to the other. Parallel means obviously the source and drain are in parallel, right? Which means the current can flow from either of these paths. And if it's series, current has to flow through these paths. And even if one of them is blocked, the current will not flow through. Now, quickly, let's look at this. Which type of logic is this? The first one you think? And let's see, what's the second one? Can some of you type in the chat?
First one is 3-input NAND.
No, let's just type in the chat. Please don't talk. Just type in the chat. Okay, 3-input NAND. Okay, 3-input, obviously, because there are 3 inputs. Why is it a NAND? We'll talk about that. I think we've seen that in the truth tables. And then what about the second one? Some people are saying it's a second one was a 2-input NOR, and then some of you said it's a 2-input NOR. No. Okay, 2-input NAND. Okay, it's actually a 2-input NOR. I think a lot of you have got that right, and that's right. This is a 2-input NOR gate, and if you start plugging in the inputs, you will realize. Let's take this one for example, right? You apply 1, 1, 1. What do you expect to see? So 1 is going to turn on the NMOS, turn on the NMOS, turn on the NMOS. So all 3 are on, which means current can flow from ground to the output. But because it's a complementary CMOS, because as you notice, PMOS is on the pull-up side, NMOS is the pull-down side. Both of them cannot be on together. So when you have 1, 1, 1, these are off. So the output is connected only to the ground. And since all 3 are on, you have a low resistance path from output to ground, which means this goes to 0, which means 1, 1, 1, this goes to 0, which is good. But I have to check other conditions. I make it any one of the inputs to be 0 now, which means the pull down is not going to be active at all, right? Because it's a series path, which means the current has to flow, means all of them have to be on. So if any one of them is 0, the path is only from any one of the transistors on the top, which means any input is 0, the output is a 1, and that is nothing but a NAND gate. So you're right. So it's a 3-input NAND gate. I can repeat a similar analysis here. And what I notice is I see the PMOS is in parallel. I see NMOS is in series, which means obviously it means that since PMOS is in series, the output will flow to 1 only if both the inputs are 0. And since NMOSs are in parallel, the output will go to 0 even if any one of them is 1. So this is a NOR gate, and since there are 2 inputs, it's a 2-input NOR gate. So let's give this a try during the break. Just take this, note this down at your end, and let's give a try. And maybe if you have any questions, we can discuss this during the break. So let's talk about this. So is it possible for you to build a CMOS and an OR gates just with single stage? What do I mean by single stage? So this is called as a single stage thing. A single stage means just from the supply to the, so if I make this a black box, so there's an input and there's an output, right? But if let's say I make the box transparent, it's not a black box anymore, and let's say it's a glass box, and I can see that from the input, I can directly reach the output just in one level or one stage. One stage means there is only one group of pull up devices, and they're not second stages and third stages and fourth stages and so on, right? So there's only one level or one stage of pull up pull down transistors or devices. Then it's a one stage logic gate. So can you build an CMOS and or an OR just with a single stage logic gates? Can you just give a try and tell me how the topology would look like, how the arrangement would look like? If the question is not clear, please type no. I can try to explain again. So is it clear what I was trying to explain about what a single stage network is? A single stage network. So this is basically, if I look at this is a single stage network, single stage logic gate. Single stage because from the input to output, any one of the input to output, I only have one level of pull up or pull down. If I build something more complex, let's say I put a NAND followed by a NOR or in 2 inverters and 3 inverters and so on, that's like a multi-stage or a multi-level logic gate. But if it's just like this, where it's like only one pull up and one pull up and pull down stage from the input to the output, then it's a single stage logic gate. Both of these are single stage logic gates. So I'm asking, can you build CMOS and NOR gates using single stage logic gates? Can you give a try? Okay, I think we can discuss more during the break. So it's not possible for us to build CMOS style and or OR gates using just single stages. Why? Because a CMOS style logic gate is always going to be an inverting type of logic. As you notice here, when any one of the inputs is high, or all of them are high, in this case, the output is a low, which means when input is high, output is a low. And then when input is a low, output is a high. And you look at any combination of inputs and outputs is always trying to have an inverting behavior. So CMOS style pull up, pull down type logic gates right? A CMOS style gate will always be, a single stage is always inverting. And because a single stage is always inverting, you can never implement a positive logic like an AND or an OR using it, because of the fact that AND and OR requires input is high, output needs to be high. Input is low, output needs to be low. So you cannot do that in single stage. So you need to actually then, how do we do it? You will have to cascade or put them one after the other. So CMOS style, as I said, cannot build a non-inverting single stage gate. You'll have to put them together, which means AND can only be implemented using NAND and an inverter. So it also it sort of explains why AND is not really we know that NAND is actually a universal function and AND is not. Why? Because unless you have an inverter, you can never use an AND to create inverting logic. Whereas without even having an inverter, a NAND can work, because when you short both the inputs, a NAND behaves like an inverter, right? So any positive logic and or will always or a buffer will always require two levels in the CMOS style logic gates. Okay, so we are ahead of time. We still have, I think, 5 minutes for the break. So let's start. Open up the discussion. If you have any questions, you can type in the chat, and we can I can try to answer them. Any questions?
For NOR gate also, we can use the same concept, no, sir? Like NOR followed by NOT gate.
Yeah, not followed by NOT gate is basically a buffer.
OR gate.
Yeah, for OR gate, yes. NOR followed by inverter will be a OR gate, yes.
What about other gates, sir?
So let's take an example. Give me an example of some other gate, which is a positive logic.
Other than AND gate, for example, if you want to have XOR gate implementation, how could it be done?
So XOR gate implementation again is, you can, so what exactly is XOR? Right, XOR is A bar B plus AB bar. So which means you cannot implement that just with a single stage, because you need inverters for that separately, and you have to generate A bar and B bar signals, right? So the way, I mean, the CMOS style logic gates have to be implemented is, you have to think about the logic, implement that in the pull down network. So A bar B and B bar A, right? So you think about that, implement it in the pull down network. And when you implement that, so what's going to happen? When this logic condition is true, the output will be what? Will be a 0, which means when you implement an XOR type of logic, and then the conditions are true for the XOR, which means A is 1, let's say it's a 2-input XOR, A is 1 and B is 0, or A is 0 and B is 1. And if that's the logic you have implemented in the pull down, and the output will always be 0 for that. Why? Because it's a NMOS based network in the pull down. So which means if you want to actually implement an XOR, you need to have an XNOR type scheme here, and you need to have an XOR here. So that's how, I mean, the complementary CMOS logic style. I think we'll probably discuss that, and we can try to implement some gates. But basically, that's the whole approach of a CMOS style complementary network. So you're going to have some logic which needs to be inverting here, and then, so which means, why, if this is output bar is nothing but when input is true, these conditions are true. Why? Because when these conditions are true, you create a connection from pull down to output, and it's a logic low, which means output bar is actually a high. And if you want to get output to go high, so you need to have a specific arrangement in the PMOS. And then for those set of inputs with inverting settings, you're going to have a connection from VDD to output, which means output is now going to be for those inverting inputs. You will have some logic condition here, and that's going to be true. We can discuss that maybe after the break. We can try to implement an XNOR and try to.
Arun sir,
Yes, sir. Go ahead.
because most of the inputs, when we go for XOR or XNOR gates, our inputs will be a complement form.
That's correct.
So whether we can call it is a two stages or a 3 stages, because the complement also we have to put an inverter there.
Yes, you need to have an inverter because with,
Yeah.
as you rightly said,
Whether we call it is a 3 stages or still we call it is a multi-stage.
it will not be single stage, obviously, as you said, because we require the A bar and the B bar signals,
Ah.
right? So you need inverters for it. So it's not really a true single stage CMOS. You require
Because input also complemented, there we are connecting an inverter.
Correct.
Again, there is a pull up and pull down. Again, we are adding a one more inverter at the end. So
No, we
whether we
don't-
call it is a 3 stages or only the 2-stage design.
You can build it in 2 stage also. If you're building a
Yeah.
2 stage, what you need to do is you need to have an XNOR in the pull down and you have an XOR in the pull up.
Okay.
So you have to have the complementary logic. I think once you would do that, you can build it in 2 stages. But it will not be, you cannot do it in single stage, as you said, because we need A bar and B bar, which means you need a separate inversion for A, and you have a separate inversion for B. So both the inverters have to be present.
Okay. Okay, sir. Thank you.
Someone asked the question, what is the reason behind the number of gate inputs to CMOS usually limited to 4? I think that's a good question. We'll come to that in the next section. It's basically because of the fact that when you have, let's take an example. Let's take it's a NAND 4. So Sri Lakshmi, do you want to unmute yourself and ask this question? Why you think, where you have observed this? Maybe we'll discuss this. Do you want to unmute yourself and ask this question?
Sir, I read this question in interview questions, sir.
Yeah.
Easy interview questions.
Okay, so let's take an example. Let's take it's a NAND 4. A NAND 4, let's say we know what a NAND is, right? As we saw here, this is a NAND 3, as we're seeing here. This is a NAND 3 because NMOSs, 3 of them are in the pull down. So 3 of them in series. If it's a NAND 4, which means you will have one more input and one more NMOS device here and a PMOS device in parallel. So what will you see there? You're going to see 4 NMOS devices in series. What happens is, as you start putting more and more devices in series, the gate becoming the gate's delay becoming pretty bad. And what happens is that all these transistors now, their behavior is not very sort of comparable. The device which is fairly far away from the ground will have a different gate to source or gate to body voltage, and similarly the other ones, the ones which is closest to the ground, is almost like an inverter in a NMOS. But ones as the ones which are going far and far away, their behavior is significantly different from the ones at the bottom. So what that does is that the delay is not going to scale well, and you will have a significantly worse delay even if you start upsizing the devices. So let's say usually what do we do when we size these logic gates? We want to match the delay of this very closely to an inverter, right? So if you're going to have 4 transistors in series or 5 transistors in series, you will have to upsize or make this significantly bigger so that the effective resistance from supply, the output to the ground, is minimized. That starts becoming more and more, and you'll have much bigger gates, and their delays do not scale well with respect to inverter. And that's why people, especially when we have standard cells, we'll talk about it. And you have standard cells which are like fixed template type of cells, we do not have gates even more than 3 inputs in a lot of libraries. 4 sometimes, but usually it doesn't go beyond 3 because it's very expensive to build those gates to have good delays. But that's a good question. Any other question?
This 4 input gate also give effective results, sir?
No, you can build 4 input, but again, it's going to be, you need to size these transistors fairly large for it to have a similar delay as an inverter. Or if you compare the delay difference between the pull up and the pull down, there will be a big difference between the rise and the fall delays. Why? Because the rise delay is just through one transistor to the output, whereas the fall is through 4 transistors. So there'll be a big delay difference, and which means it's not a very effective gate on the path. So if you have a timing path, or if you're putting a lot of gates on the path, this circuit will have a very poor delay behavior. So that's why people avoid transistors with more than 3, or in some cases 4 transistors. They don't have any other gate which is more than 4 transistors in series. So that's why more than 4 input gates are avoided.
Thank you, sir.
Okay, any other question?
So how is DSP related in VLSI type carrier, sir? Like signal processing or data communication? How it is important, sir?
So DSP as a field is different than VLSI. DSP, if you look at it, it's about signal processing. But to actually implement DSP, you need to have an FPGA or an ASIC or a software or one of these approaches. So if you just talk about the pure DSP field, your pure DSP is just about signal processing. So it has got to do with statistics. It's got to do with signal characteristics. You must have studied about signals and systems and all these aspects, right? So statistics, sampling, all these topics are covered in signal processing. But to actually realize or implement them, you need either FPGAs or ASICs or even software-based approaches to physically implement those algorithms or the DSP systems. So they are independent. If you're actually trying to build a DSP system, yes, there will be some VLSI aspect to it or a system aspect to it. But if you're just looking at algorithms, then that's a different field. Does that answer your question?
Yes, sir. Thank you, sir.
So Bhaskar has a question. Just a minute. I think I'll just quickly go over Bhaskar's question. Bhaskar, you want to unmute yourself and ask the question?
Sir, since AND and OR gates have extra stages, it would create more delay for the gate. So would it be more efficient if we convert the Boolean functions into NAND and NOR?
Yeah, that's a good question, and that's something which obviously, since we say that AND and OR require 2 stages, which means it seems more expensive to build an AND and OR. Can we just use NAND and NOR for logic? And that's actually people have talked about this. A lot of people try this out, and yes, that's something which can be explored. But what's also interesting is we're going to talk about delays of these logic gates, because I didn't talk about that. I just talked about implementing these logic gates as functions, and I'm just talking about its logical behavior, how it's working like switch. But in reality, in a physical implementation of a logic gate, we have to worry about delays and how the delay is affected. So we're going to talk about that. But quickly, if you notice, this is a 3-input NAND. The 3-input NAND is going through the worst delay, whether it's rise or fall. What is rise delay? Rise delay means what is the time taken for the output to go from to when it is currently at logic 0 to go to logic high, which means the path is through the pull up. And logic low will be fall delay will be when the output is high and it is falling down to 0 because the pull down network is high. So if you notice, the pull down network in the case of a NAND is going to 3 transistors, which means there's a lot of resistance here, because each switch is going to have a resistance. It's not a metal, right? A transistor has almost 100 to 1,000 times more resistance than a wire, just a simple wire. So even though it's a good switch, but its resistance is not like sub ohms. It's not like 0.1 ohms, or it's probably in the 100 to sometimes even kilo ohms. It's kilo ohms, depending on what state it is in and what type of transistor it is and so on. So therefore, if you have more and more transistors in series, you're going to have a high resistance here. And finally, the delay in a switch I am going to talk about this, but quickly is that a digital circuit, you can completely approximate it by an RC circuit. What is RC here? The switches or the transistors, when they're on, they behave like resistors, and the output is going to behave like a load, which is a capacitor. So because it's an RC circuit's delay is proportional to R into C. So what you will notice is that even though the NAND is good from an area point of view, because I just need one gate, but its delay is very sensitive to the output load because it's going to 3 transistors because the resistance is high. So which means I cannot make this and a NAND gate drive a long wire or too many gates because the delay is going to start increasing fast. So therefore, when you put an inverter at its output, what that does is that if I keep this inverter very close to this NAND gate, I can get an AND function, but I can, because the inverter is the best circuit in digital logic to drive a lot of load. So I can use this to drive longer distances or more gates. So therefore, it becomes a trade-off. And you have to think about what's a good way to do this trade-off. So the question is valid, but it all depends on condition. If you don't have, if a logic or a design does not have very long wires or places where I have too many loads, then yes, I can do with NAND. But I have a lot of places where I need to drive a lot of load or a lot of wire. NAND will have to be replaced. It has to be an inverter on its output. So yeah, that's a good question. I think that sort of comes up when you start designing a system. Does that answer your question?
Yes, sir. Thank you.
Sir,
Yeah, go ahead.
sir, which gate consumes very less power, sir?
That's a good question. What do you think? Which gate consumes the least amount of power? You give me the answer. So anything which has small number of inputs, a smaller number of inputs, we're going to consume less power, right? Which means the inverter is going to have the least amount of power. But the question to ask is, what is the use of an inverter? Inverter is basically on its own is a useless circuit. Why? Because it's only telling me yes, no, yes, no, yes, no, right? What is the use of yes, no? I cannot build any complex logic with it. Therefore, I need multi-input gates. So even though inverter is the gate which has the least power, finally, when I talk about power, I have to talk about what function I'm going to implement. Let's say I'm going to build some sort of an adder, or I want to build some sort of a complex logic to do some operation. For that complex logic, then I have to decide which type of gates I need to use. So someone asked the question, why can't we use 5 input gates? And that's where you start seeing that when you start using 5 input gates, because the delay is very bad, you may not meet your performance requirement, and therefore you'll have to upsize these or make these devices bigger. And therefore the cost of using these bigger gates starts hurting your power. So to answer the question, there is no gate which is good for power. It all depends on what is your use case and what is your functionality. And for that functionality, you can decide how to use the best gates. So we're going to talk about that maybe in the coming days.
Okay, sir. Thank you.
Okay, I think we are just 2 minutes away from 8. If there are no more.
Yes, sir.
Yeah, go ahead.
Christmas.
This is Chandrasekhar from Mysore.
Yeah.
Yeah, I need a clarification that we say that when we take any designs in a VLSI, these 3 factors are the major part. One is with respect to the power, and one other is with respect to the area, and finally with respect to the speed or a delay. So I want an answer that why we can't compromise all these 3 factors. So the theory says that if you want to compromise with the power, we need to not worry about the area and the speed. And if I want to concentrate on the speed, we can't able to achieve we can't able to have the area like that. That is only the 1 or 2 factors will be compromised. Why not all the 3 factors cannot be compromised or what? So is there any issues with the structure or with the fabrication process?
Yeah, that's a good question. I don't think it's got to do with structure or fabrication process. Let's try to put this in a different form, right? It'll be like a
Okay.
very it'll be like a layman way of looking at it. Can you just mute yourself? Okay, so we'll talk about it in a very layman sense, right? Now, when you go to buy a car, the car has a certain mileage, can give you some acceleration, can seat so many people, which means has some volume. When you go and buy a car, let's say the car designer, think of the car designer as a CMOS circuit designer or system designer, right? Now he comes to you and says, sir, take this car. We did not care about trade-offs. It is small in volume. It gives very poor mileage, and its acceleration is poor. So I have not worked in the trade-off. And this car, I mean, you can buy. Will you go ahead and buy that car? Okay, you can unmute yourself. Okay, will you go and buy that car? You can unmute yourself. Yeah, so obviously you will not buy that car, and that's again, it's not like you don't want to trade off or you don't want to have these constraints, but these constraints are not coming from me. If given a choice, I will not have these constraints, and I will take the easy route. But my competitor or someone, my customer, will come back and say that person who's giving me this product gives me lower power for the same performance, or gives me lower power and more performance, and or he would say he gives me more performance at lower cost. And there are so many different combinations possible, and each one of them he's going to fight for better results for him or better trade-off for him. Same way as you argue with a shopkeeper or a vendor who's selling you some services or he's selling you some product. I mean, same thing applies here. These choices or these trade-offs are not because they cannot be made, but these are being made because you want to know what is the best possible you can do. It is true that when you have to meet some performance, you are going to pay some power penalty. But that's where I think all these engineering and design tricks and concepts and techniques come in, which you have to understand well to be able to build a good system. I can always say, I'm going to run at 1 hertz. I'm going to consume a huge amount of power, and I'm going to consume a huge amount of area. Who's going to buy your product? You will not even survive one day in the industry because there are people who are doing better than you. So you have to improve basically because, or you need to know better methods and techniques because of the fact that customer or the competitor is doing it. And that's basically the reason. So all these methods or discussions that we are having is basically because finally you need to know these best methods and or the well-known methods, and we are trying to implement that. Hopefully that answers your question. So it's not a technical question. Yeah, it's not a technical question. It's basically because of the fact that it's driven by how trade-offs are happening. It depends on how optimization is happening. It's like economics. It's actually not technical. It's primarily driven by economics. Someone gives you a better product, you will go for that, right?
Yes,
not because, yeah. Okay, so we run out of the time for the first break. Now we'll resume. So let's move on. So let's quickly talk about some of the delay aspects of CMOS logic gates. So as we said, these are electrical signals, and primarily in CMOS logic gates, the signal that we care about are is the voltage or the output voltage and the input voltages. So let's say the input voltage is some waveform which looks like this. And usually in a lot of the textbooks and in general, when we do a very pencil paper analysis, we are assuming the waveform is like a rectangular waveform, very neat logic levels, and rise and fall times are sharp. What is rise and fall time? Obviously you would know. Rise time is, as I said, going from logic 0 to logic high. VDD means logic high, 0 voltage means logic low. And then you can go from logic high to logic low. So this is called the fall time. And then what exactly is delay? So I talked about stages, right? In the CMOS gates, I talked about single stage and the multi-stage and so on. What is a stage delay? Stage delay means, or the propagation delay is nothing but the delay when an input undergoes a change, it is triggering a change on the output. That delay for that stage is called the propagation delay, or the so in this case, the propagation delay through a single stage, or if you're talking about multiple stages, if it's a multiple stage, let's say if it's a multi-stage gate like this. So when I change the input, and then through when the signal travels through all these gates and then causes a change on this side, again, change in input triggering a change in output is the propagation delay. So this propagation delay, when the signal goes from low to high or high to low, is being shown here. So what is being shown here is that when the input is going and reaching the 50% level, and the output when it's changing to its 50% level, we measure the propagation delay. And the propagation delay is from high to low. We call it, in this case, it's called TPHL, which means propagation delay for fall time, or high to low. Right? And then similarly, from the 50% point where the input has changed or fallen here, and output has risen to 50%, that is propagation delay for low to high transition. That means what is low to high? The input going low and the output going high. In this case, output going high, that's why the H is here, and the input going low. So if there is a continuous input change, like a waveform which is going up and down, like a cycle, right? Or a clock, as a cycle is sometimes also called, then the output will also change if it allows that signal to cause a change on the output. Then there is, because you have one instance of a high to low followed by another instance of a low to high to come back to the same level. If you notice, we started at a high level, we come back to the high level. So we've gone through two transitions, one high to low, one low to high. So there is, since these two may be different, how do I get an average metric for the whole cycle? So it's called an average propagation delay, which, as an average implies, you're going to take the high to low and the low to high, and you take an average of that. Sort of an obvious way of doing it. So this allows you to not worry about whether it's a high to low transition or a low to high transition. You just worried about an average number, and you can say, okay, how do I minimize this average number, or how do I increase this average number, and so on, right? So this is propagation delay. Propagation means from the input to the output. So there is another metric which is called the rise time or the fall time, which is called transition time. Transition time means the signal with respect to itself. So if I take just the signal output and I look when it has changed from some level on its input to another level on its on the same signal, let's say from 10% point to the 90% point, right? Let's say the input is going from low, so that the signal is going from low to high, right? Signal is going from low to high, and I'm looking at the point where the signal reaches 10% point, which is like somewhere here, let's say, and then the same signal as it's going up, it reaches the 90% point, 10 to 90. I can call this as a transition time or the rise time. Because why rise? Because the signal is rising. Similarly, I can have a fall time. What's going to be fall? I start from the 90% point where the input has fallen to the 90% of the logic high, and to the 10% of the logic high. That is the fall time. Why fall? Because signal is falling. There are multiple ways, and different companies and different teams and different methodologies have different definitions of rise and fall time. So what is different in the definition is not what I explained, but what is different is only at what levels you care about, and what levels you care about to call it a rise time or a fall time. So for example, most people who are doing circuit design will talk in terms of 10% to 90%, because that covers a big percentage of the signal. So 10%, 90% means what percentage of the signal is being covered here? Can people type in the chat? 80%. That's right. 90 minus 8. 90 minus 10, right? So we're covering 80% of the signal, which is a significant portion of the signal. So a lot of circuit designers use this metric. But a lot of ASIC based flows, they don't use 10% to 90%, and they actually use a 25% to 75%. So if it's 25% to 75%, what's going to happen is this point sort of shifts slightly up, and this comes down. Okay, as someone rightly said, 25% to 75% covers 50% of the signal. So depending on who you talk to, which teams, which designer, what flows they use, the definition of rise time and fall times could be different. But one thing is clear: if it's rise time, the signal is going up. Fall time means signal is going down. And if it's propagation delay, it should be clear that it is from the input to the output. And high to low means input going high and output going low. Low to high means input going low and output going high. And you could also have a high to high or a low to low as well, depending on if such combinations can exist. And we talked about the average delay here, right? So now, so let's talk about the delay aspects of CMOS logic gates. As I was saying during the break, that we can approximate a CMOS switch, which basically are transistors, and effectively the gate into nothing but an RC circuit. Each switch can be converted into, or approximated. I shouldn't say converted, because this is more like a mental model. What is a mental model? When I say mental model, it means a very simple thumb rule or an approximation that allows us to analyze these circuits quickly. Obviously, when you have very complex behavior, you would like to run a circuit simulation using tools like SPICE, or you want to use more accurate models. But if you want to just analyze and do a quick approximate analysis, or you want to get to see how the general behavior is, understand the concept, you can approximate a switch with or a transistor with a resistor. So depending on which transistor in a CMOS pull up or the pull down is on, all of them could be converted to resistor. So the one which is with the side which is on can be converted to a resistor. The side which is off will be like an open switch because it's cut off. No current flows through it. Now, so in this case, if it's the pull up which is on, as I said, in a complementary CMOS, either the pull up is on and the or the pull down is on. In this case, pull up is on, which means pull down is going to be off. So it's open. So no path from supply to ground, as shown in this approximate view. So this inverter is approximated with this RC circuit. So all the off devices are converted into switches and open switches. The on devices are converted into resistors, and the load is converted into a capacitor. So effectively it's an RC circuit, and we know that if you remember your RC circuit concepts from your network analysis basics, probably covered in your second year, right? Maybe third sem or fourth sem, I don't remember when it was, but hopefully in the second year, then you would remember that the delay of an RC circuit is directly proportional to R into C, right? So even though if you look at it in very lot of detail, the RC circuit, the actual delay will be a very complex function. But for most uses or most analysis, just the product of R and C is good enough for you to understand how whether the delay is bad or the delay is good, right? And that's what a lot of really good circuit designers use, digital circuit designers use to analyze whether the gate is going to be good or gate is going to be bad. How do we size this? How do we optimize it? And so on. So that's like a good method which you should remember and try to practice if you want to compare gates. Let's say you want to compare, for example, we talked about AND 4, AND 5, NAND 4, NAND 5, NAND 4, NAND 3, and so on. Just convert them into resistors and you will start thinking and you'll start getting a good picture of what it is. And how do I look at delays? I just look at R into C. What is R into C? What is the total number of switches here? All of them which are on, convert all of them into resistors, and then output has a load which is converted into a capacitor. What is the effective resistance on the pull up or the pull out, pull down? And then find the effective, I should say, rather than saying effective, I should say the worst case resistance. The worst case resistance on the pull up or the pull down, and the load on the output, multiply those two, that gives you a good approximation for the delay. Now, when you start looking at it in more detail, now we talked about where the propagation delay in the previous slide, how it is from input going 50% to output going 50%. So in reality, what exactly is happening is that at the 50% point, what's happening? The load on the output of the CMOS gate, this capacitor, has charged to its 50% of the final value, which means if it is going high, which means it's reached VDD by 2. And if it is at going down, it's discharged from VDD to VDD by 2, right? So that's what the propagation delay is in a sense representing. So the actual formula could be an approximation of half the time it takes for the load capacitor to reach the time it takes for the load capacitor to reach half its charge, right, or VDD by 2. And then what is the drive current of the resistor or the switch? And then if you start plugging in actual equations, you know that the equation of the MOSFET's current is proportional to VDD square, VDD minus VT, or VDD plus VT, depending on NMOS or PMOS. And there's a dependence on the width of the device, the length of the device, mobility, the oxide capacitance, and so on, right? The gate oxide capacitance. So effectively, this becomes an approximate or very close to the actual formula of the delay of a CMOS gate. Now, there are so many different parameters here, so it becomes very difficult for you to understand the effects of all of this. Some of them are in your control. Which ones are in your control? I'm going to talk about that. For example, width and length could be in your control. VDD could be in your control, but the others may not be in your control. So it becomes very difficult, and that's why this whole RNC based approach becomes very simple for you to analyze and discuss in that lines. But if you want to get into more details and understand all the parameters or variables controlling the delay, it's basically going to be these: the load capacitance, the supply voltage, the threshold voltage, the mobility of the transistor, of the holes, depending on the PMOS or NMOS, and then width and length, the oxide capacitance. And obviously, this is a function, and there are directly proportional variables. There are inversely proportional variables, as you can clearly see. As you can see, when the supply goes up, what do you expect to see? The delay is going to go down, right? And then, so what's going to happen is that you have a trade-off to make. You can try to, but the supply also increases the current, right? Which means there's probably more power here because power is directly proportional to current. So what do? I can speed up the circuit if I increase the supply, but I have to make more in power. So which means I may have to find a good balance between power and this. As someone was asking about trade-offs, why can't we do this? This becomes one of the trade-offs to explore. And this is actually a very frequently used, even for example, I frequently use in my when I'm trying to architect something, I will have to decide whether can I build this product at this voltage? Can I get a better voltage or a lower voltage for the same performance? If I have to do that, what do I need to do? And so on. So this is like a very important parameter or a design architectural and a system parameter. Channel length, as you can see, the channel length has an influence on the current. Current has an influence on how quickly you charge or discharge. And therefore, channel length is directly proportional to the the delay. Smaller the channel length, effectively, it means that you have a smaller resistance of the switch or the MOSFET, and therefore you will have a smaller delay. A wider transistor also allows you to reduce the resistance, which means that's going to have an inverse dependence on the delay, and so on. But all of this, a wider transistor is going to mean that I'm going to have more load here, which means more capacitance on the input side, which means more power. So all these are trade-offs, which a circuit designer and a system designer or an architect will have to do when they start looking at VLSI systems. So we'll talk about this during the break. This is sort of an interesting data point and a concept which I think will be good for you to internalize. We'll cover this maybe in the break. If you have any questions, we'll come back to this. So I was talking about, so I plugged this equation again here for our reference. So let's look at when I was saying different parameters. So some of the parameters are in your control and some of them are not. For example, when I'm designing or architecting, I need to know which one is coming from the fab or foundry and which one is controlled by me as an architect and which one I'm controlling as a designer. So when I say architect, I mean like a system. And when I say designer, I mean in terms of circuits. So which one is technology? Which one is architecture or system? Which one is design or layout? So I've sort of put some of them here. So if you come back and look at this equation, let's try to see. So mobility, which is mu here, this one, oxide capacitance, which is here, threshold voltage, channel length, at least the minimum channel length. And if it's a FinFET, the number of fins per transistor. And then if it's a wire load, the minimum wire width and spacing. These are completely controlled by the foundry. The designer, the architect have no role to play here. This is completely coming from technology. This cannot be modified. So which means I have no flexibility in controlling those parameters. But if I'm an architect, what can I control? I can control the supply voltage, and supply voltage is a very strong and a powerful parameter because if you have lots of transistors running on the same supply voltage, a chip I said could have a million billion transistors. So therefore, I have a opportunity to influence million billion transistors switching by controlling what this voltage is. So therefore, it's a very strong parameter and probably one of the most important parameters. So an architect or a system designer can control this, and he has control on this. Some aspect of the load capacitance, because what is load capacitance? Load capacitance depends on what kind of functionality and complexity I am building in my design. I could have some complex adder or a complex controller being built, which could have a lot of load, which means many gates are being driven by one gate, or very few gates are driven by one gate, and so on. So therefore, some part of the load capacitance depends on the architecture of the system. Supply is completely determined by the architect, or majority of it comes from the architecture. Then let's look at design variable. The design variable means something which the circuit designer or the layout designer can control, which basically means anything which is related to geometry. Or the geometry, for example, when I'm drawing layouts, right? Or layout, for example, I'm building the transistor or the wires. I'm drawing them on the layout. So the width, W, is controlled by the layout designer or the circuit designer. The number of fingers, which means how many transistors in parallel, it's controlled by the circuit designer. The block size, which means how much area I allocate to a block, will be determined by how many transistors I have, how many big and small transistors I have, and so on, is determined by the designer. Wire length. I talked about wire length even here, even here in the technology side. So some part of the wire length, which is minimum width and spacing, just comes from the technology. But if the wire is not minimum width and spacing, and how far I can drive the wire, it is determined by me as a designer. So whether I'm driving a gate, let's say by 100 microns or 5 microns or 50 microns or 1000 microns, that's completely in my control. As a designer. So that wire length is in my control. So wire length determines the load of the wire. Width and spacing, again, if I want to reduce the resistance of a wire, if I want to reduce the capacitance of a wire, it's completely in my control. I can play around with this. So it's again a design parameter here. So these are interesting variables that you have to understand to decide on the trade-offs possible at different levels. So the foundry trade-offs, the trade-offs that foundry makes has a significant impact on the overall product, because a lot of these variables depend on that. System again has a big impact because voltage and the design is completely determined by that. So as I'm coming down from technology to architecture to design, the flexibility I have to control the effect of this on the design's trade-offs starts coming down. And that's something which we have to understand. So I talked about load capacitance. Let's see how can I break down the load capacitance into more details. So the load capacitance, which is usually just approximated or abstracted by CL here, you can go into more details here and you can say that, okay, what if I'm driving two gates, two inverters here? So which means the oxide capacitance or the input capacitance of the CMOS gates have to be included, which is the CG. How many of them? So if each gate is giving a capacitance of CG, and there are n gates, which means it's going to be n times CG, depending on what's the unit gate capacitance. C wire, because I cannot connect this output to this gate unless there is a metal to metal connection here, because I told you that every terminal has a metal connection. I have to hook up this. They don't connect automatically. So some wire has to be drawn. A wire has some load because it will have some resistance and capacitance. So the wire capacitance has to be accounted. In addition to that, the gate capacitance or the input capacitance and wire capacitance, which is coming from the load. Load means something which is driving. But the gate on its own has its own contribution to some output capacitance. That's called the parasitics, the parasitic load. Because these are based on real layouts, so there's going to be some drain to body, right? And for the NMOS and drain to body for the PMOS, some loads here, maybe some coupling capacitance from the input to the output, like which is basically mirror capacitance, so on. So all of that starts accounting for this parasitic load. So these two are parasitic loads. These two are output loads. So you can break this down and you can account for it. Similarly, there will be some resistance, and resistance is primarily coming from the MOSFET resistance, but additionally also for the wire resistance which may be there. So MOSFET resistance is completely within a designer's control. Wire resistance is basically depending on how far he wants to drive. Again, in designer's control, but sometimes he may not be able to control this too much, because if the design is big, you can't get all the gates to sit close to you. You may have to spread them out, and that may add to some wire resistance. Okay, so then if you're going to talk about all these complexities, right? We talked about all these designer parameters and technology parameters, architecture parameters, and these complex formulae and so on. This is obviously, if you get into details and you want to analyze it, it's sort of possible to do. But if you want to do quick analysis and comparison, it becomes very difficult, and people cannot start writing equations all the time. Okay, this is. So there's this concept of logical effort. The concept of logical effort, I think you may have studied it or you may not have, comes into play, and it's sort of a very interesting and a very useful concept. When, let's say, you have to compare different types of gates. There are so many different possibilities of gates. And they have to compare, let's say, different technologies. Let's say 7 nanometer to 5 nanometers, or one foundry, let's say TSMC to Global Foundry, or TSMC to UMC, or let's say you want to compare one architecture, one adder type to another adder type. some architectural aspects. And then how do I know what is the best levels of logic that I need to have? How should I size them to have the roughly the same delays? How do I compare them? Is it fair to compare them? So all of these questions, which a lot of these designers would actually face, is not trivial. It's something which, because let's say you see a paper, you read a paper and someone says this is the best circuit that's possible to build for this functionality. And I come and implement something and I say that my delay is smaller. But let's say the person who built that, he built that in 28 nanometer, whereas I have built in 14 nanometers. How do I compare? I know that when I go to 14 nanometers, because it's a better technology node, it's more advanced, I'm going to be faster because I've been able to shrink my area, which means my wire load is smaller, my transistors are smaller, which means it less load capacitance. And because as I discussed, the delay of a gate is nothing but R into C. If C is decreasing and the chip is smaller, which means I have shorter wires, which means R is also reducing. Obviously, I'm going to have a smaller delay. But the person who actually reported numbers, he reported numbers at 28 nanometers, where I'm reporting at 14 nanometers. My delay is smaller than his, which is expected. And he may say that you are on the more advanced node, your delay is expected to be smaller. So how do I compare that my circuit is better than his circuit? And let's say if I want to know whether I can use his method to build my design, how do I even know how to compare that? Right? And all of these comparisons are possible using this concept of logical effort. So the whole idea is that it uses a very simple model for the delay. RC primarily, some form of an RC delay. It's an approximate or intuitive calculation. It allows people to do a rapid comparison between various alternatives. For example, I was comparing 14 nanometers versus 28 nanometers. And I think that's basically the one of the important requirements and motivations to have this whole concept of logical effort. Logical effort was developed by a person named Ivan Sutherland in the early 90s. It became very popular. I don't think it's very popular now because people don't use a lot of approximate ways of designing, because a lot of people just use standard cells, and there's not a lot of flexibility in size the standard cells. But it's still very, very useful for use in custom design, where people are free to choose the type of the transistors they can have, what's width and how many fingers, what width. So it's very useful in custom design, and it's become less effective for use in standard cell design, but still a very interesting and a good concept to understand. So basic idea of logical effort is that we are trying to compare all possible logic gates with the best possible logic gates in terms of delay. The best possible logic gates in terms of delay is an inverter. Right? For obvious reasons that inverter only has one resistance from between the input and the supply, or the input to the ground. Whereas other more complex gates, even though they are implementing more complexity and more logical functionality is there, you're obviously going to have more delay, because for the obvious reasons that you're going to have transistors in series, more transistors in series. So what logical effort is trying to do is, when it's trying to compare different logic gates, is that it's trying to give a simple way to explain or compare what is the cost of adding more complexity in a pull down or a pull up network. Or if a path has a lot of such gates, what is the cost of such gates? So what is the simple model or the approach? We'll get into the actual simple math of it, but a very quick way of doing it is look at the input capacitance of a inverter. Now, assuming the PMOS is sized twice versus the NMOS. Why? Because at least in the textbooks, we study that the mobility of PMOS is half the mobility of the holes. The mobility of holes is half the mobility of the electrons. So you will have to effectively, to get the same resistance, you have to double this device width. So it's sized twice than the NMOS for having the same rise and fall times. Assuming that's the case, then we know that the area of the gate depends on its width, and the area of the gate also controls how much is going to be the gate capacitance. Right? So you can approximately say that the area is nothing but directly controlling the input capacitance, and therefore, if you just take the width, which is relating to the area, you can say that the input capacitance is going to be proportional to the sum of 2 and 1, which is, in the case of an inverter, that becomes 3. So Cin, even though it's written as equal, in reality is nothing but proportional. So we ignore the proportionality sign because the proportionality sign is a constant for a technology. So let's say that all these gates are built in TSMC. So Cin is proportional to 3 or equal to 3 if you ignore the proportionality factor. So, and then if you compare this NAND gate, Cin for the same rise and fall delay is going to be 4. Why? Because you have 2 NMOSes in series now. So you have to size them double to get the same behavior as an inverter. So it becomes 4. For the case when you want to build the NOR to have the same delay as an inverter, you have to upsize the PMOSes to now 4 times to get effectively the same resistance as inverter pull-up. So what is the input capacitance here? 4 plus 1. For a NAND, it is 2 plus 1. When I said input capacitance, I mean each input has to be taken separately. So A is seeing a 2 here and 2 here, which means it's 4. Similarly, B and C. So you take any one of these two. So input capacitance is proportional to 4. If you take the NOR, 4 plus 1 for B, and similarly 4 plus 1 for A, you take any one of the two. So Cn is proportional to 5. So now what the whole approach is all about, you're comparing everything or normalizing. I'll keep using the term normalize. Normalize means you are comparing with respect to something which is a reference. So the reference is inverter and you're normalizing with respect to inverter, which means what are you doing? You're taking this input capacitance and you're dividing it by the input capacitance of the reference circuit, which is an inverter. Inverter had a Cin of 3, so which means the baseline, this factor or this ratio, which is called the logical effort, is going to be 1 for the inverter. For obvious reasons that it's an inverter, it is self. So 3 by 3, right? It's 1. But when you start coming to more complex circuits, which have more inputs, they're going to be worse than an inverter. Why is it worse? Because the cost to pay to have more functionality, depending on a NAND or a NOR, is going to be more than an inverter. It is 4 by 3 because input capacitance of NAND is 4. The inverter is 3. So this ratio, the normalized ratio is 4 by 3. So this logical effort is 4 by 3. Then for a NOR, it becomes 5 by 3. Similarly, you can add an XOR, you can add a NAND 3 or a NOR 3 or a NAND 4 and so on. So therefore, you will start seeing that when you start adding more and more inputs and more complex topologies where devices are in series, you will have worse logical effort. And that is expected because for you to build that whole gate to have a similar delay as an inverter, the cost that you have to pay is going to be more, right? And this is a reflection of that, which means there's going to be at least this overhead on the delay for this circuit. So this is captured here. I'm going to skip this. But how do we, all this is good, but in reality, this whole simple form of 2 and 1 is not always true, right? For example, in some of the latest technology nodes, this mobility ratio is not 2:1, it's very close to 1. So how do we do it as in case? Let's say I don't know the mobility ratio. In that case, how do I do? So it's very easy to actually do this in a very systematic way. And this is what I usually do if I want to analyze, because I don't remember this formula. And sometimes I get confused, but I do understand what this picture, or if I want to do it systematically, I do it this way. What do? I take an x-axis. I have a y-axis. X-axis, what do? I take some output load on the gate's output, and I can keep changing the load. I can make it 0 femtofarad output load, 1 femtofarad output load, 2 femtofarad, 3 femtofarad, and so on. I have that output load, but I normalize the output load. What does normalize mean? I reduce the output load or divide the output load by its input load or input capacitance. So let's say if my input capacitance is 1 femtofarad and my output load is 0 femtofarad, which means my this x-axis point, which is called electrical effort, is 0. Or let's call it the normalized load or the normalized capacitance is 0. Normalized means my reference capacitance is input capacitance. So if I have no load on the output, logical the x-axis point is 0. When my output load is same as my input load, it is 1. When I double the output load compared to my input load, it's going to be 2, 3, and so on. This ratio or these points on the x-axis represents what is the ratio of my output load versus my input load or capacitance. So input capacitance 1 femtofarad means this point is actually 5 femtofarad if in terms of load. This is 4 femtofarad. And let's say my input capacitance was 0.5 femtofarad. What would it mean? It would mean that this load is actually what is going to be 2.5 femtofarad, because if my output is 2.5 femtofarad and my input is 0.5, my ratio is 5, and so on. And I fix that, and what do? I run a circuit simulation. I apply some inputs and I measure the output delay, the propagation delay from the input to the output. And I run the simulation for all these points. In this case, there are 5 points, let's say, and I run the simulation for all the points. What am I going to see? I'm going to see a set of points which are very close to a straight line, approximately a straight line. It's not exactly a straight line, but very close to a straight line. And what do I see? I'll see that, let's say if it's an inverter, let's say it looks like this. The curve or the line starts not from 0, but on some point on the y-axis, right? That means there is an intercept on the y-axis. And then as I keep increasing the normalized load to higher points, the delay is increasing as expected because delay is proportional to R and C is increasing. So the delay is increasing, and it's increasing by a fixed step, roughly. What is that fixed step? The fixed step is nothing but my slope, right? So which means this line is, as you would have studied in your coordinate geometry or basic geometry basics, straight line equation is y is equal to mx plus c. M is my slope. C is nothing but, what is C? C is my intercept, right? Which means when x is 0, what is the value of y? So y is equal to mx plus c. So I can measure the slope and I can measure the intercept. What is the intercept telling me? The intercept is telling me that even if I have no load on the design, on the gate, there is still some delay. And as I was showing earlier, that's because I have no load from the design, which means CG is 0, CY is 0, but I still have these because this is self-loading and it's called parasitic load. And this is going to contribute to some load on the output. So there will be an RC because of this, R of the transistors, and C coming from here, and that cannot be eliminated. So therefore, there is always going to be some delay, even if the output load is not coming because of gates being driven or wire being driven. And then as you start adding real load because of gate being driven or wire being driven by these normalized points, you will see delay is going to increase because there's an RC delay increase which is happening here. So this slope is representing what is this rate of increase of delay with increase in capacitance. What is interesting is if I draw this line for an inverter and if I draw the line for let's say more complex gate like a NAND, what do I expect to see? I expect to see that the slope of the more complex gate is going to be higher than the inverter. And this ratio of the slopes is also called the logical effort. This is a more mathematical way, but a more precise way of defining logical effort. Logical effort is nothing but if I get a straight line equation for an inverter, and if I take a straight line equation for a other complex gate, the ratio of slopes, or that means the rate at which the delay increases with capacitance increase, is that ratio of the slopes of the complex gate with respect to the inverter is called the logical effort. Okay. So you get these equations, y is equal to mx plus c. You can get the slope for the inverter, get the slope for this, get the ratio of the slopes. In this equation, so notice this, they call this x-axis point the normalized load, or the ratio of output load to the input load capacitance is H. And then G is the slope term, P is the parasitic, the intercept term. And then once you do this, you should be able to find logical effort. Try this out at your end, and maybe if you know how to run Spice Sims, give a try. If you have some gates you can build, maybe we can discuss this either tomorrow or maybe in the coming days in some of the breaks, or maybe on the last day, I can give more specifics. I can probably try to run some simulations if possible and show how this looks like. So let's give a try. And I think that's mainly it for today. We are nearly out of time. And this is sort of captured here, and then you can run this and give a try here. But basically, the whole idea is plot the delay versus load, normalized load. It means output load by input load, output in some femtofarad divided by input in some femtofarad. Take those terms on the x-axis. Output is delay. Plot the straight line for the inverter. Plot the delay line for the other gates. Get the slopes. Ratio of the slopes of the complex gate versus the inverter is the logical effort. So when you get the logical effort, you will be able to see that the more complex gate will have significantly higher slopes. Like for example, an XOR will have an even higher slope. An AND 5 or a NAND 5 will have even greater slopes than a NAND 2. For obvious reasons that there are more transistors in series there. And if you want to get a similar delay to an inverter, you have to invest more to get the delay down. If you don't do anything on its own, because the gate is more complex, you're going to have a faster increase in delay because of those gates. So we'll end here today. So let's open it up for some more questions. Yeah, feel free to ask questions. Let's discuss. Yeah, someone asked, intercept is equal to inherent delay. Yes, inherent delay is also sometimes called parasitic delay. That is right. So there were a few more questions. So transition time and propagation time has the same meaning. No, transition time and propagation time are not the same. Transition means for the same signal, high to low. Propagation means from the input to the output. So when you talk about gate delay, it actually, the other term for that is propagation delay. When we say slew, some people may sometimes call transition time a slew. Transition time means how fast the signal is rising or falling. That is transition time or slew. Niju asked this question, when you optimize delay, what about power dissipation? That's a good question. So we're going to talk about this maybe in the coming days. So when you optimize for delay, sometimes you have to pay a penalty in terms of power because you probably have to use bigger transistors, which means more capacitance on the input, which means the previous stage would see higher load. And since the power or energy of CMOS is proportional to the capacitance, you will have to pay some extra penalty there. What about leakage currents in the load capacitor? So leakage current, so capacitor on its own does not contribute, but the fact that the leakage current is not because of the capacitor, but primarily because of the fact that the gates are not ideal. There could be some junction tunneling based leakage currents, but that's usually very small. But yes, it does exist. It's possible, but it's not because of the load capacitor. It's basically because the transistor is leaky through the gate. So logical effort and electrical effort are the same? No. Logical effort is the slope. Electrical effort is, let's we go back to this plot. The electrical effort is nothing but the ratio of the output capacitance to the input capacitance. So electrical effort is more related to capacitance ratio. Logical effort is more related to the functionality or the complexity of the gate. So the slope of this line is logical effort. The x-axis points are the electrical effort. Hopefully that answers the question. So how do we design a buffer with a specific delay using CMOS? Yes, that's something which depends on what your delay target is. So we will talk about that maybe tomorrow when we talk about how to characterize and so on. So you can obviously decide on what, let's say, delay you're targeting, and you can try to change the load that you want to drive. And based on that, if you want to drive if you want to get a faster delay, which means a lower delay, you have to have a smaller load or a faster transistor, a bigger transistor. If you want to have a more delay, you can have higher load or a smaller transistor, and so on. So Manushri asked, can you brief out mirror capacitance? I'm not sure. We'll probably discuss this. Manushri, you want to unmute and ask this question? It's not clear what you mean by mirror capacitance.
Yes, sir. I'm asking about that. I don't know exactly what about it.
It's not clear to me what mirror capacitance mean. Oh, you mean, okay, I didn't mean mirror. I meant Miller. Miller is M-I-L-L-E-R. So there's this Miller effect. Have you heard of it in your electronics? You must have studied about it in network analysis. Have you studied this Miller effect? M-I-L-L-E-R.
No, sir. Actually, no.
Yeah, if you go and check your textbooks, Miller effect will be there in your electronics and network analysis textbooks. It says that if there are two nodes and between which there is some capacitance, the capacitance value which actually shows up on the output or the input sides depend on what is the ratio of the gain on the between the signals on the two sides. So the Miller effect is basically increases or decreases the capacitance that you will see.
Okay, sir. Thank you, sir.
So delay is more than what about the gate leakage current? If the delay is more, there is no direct relationship, but usually what happens is if the delay is more, which means the gate is smaller or the transistor is smaller, which means the leakage current could be smaller there, because the leakage current depends on effectively the width of the transistor. So smaller the width, the current is sort of proportional to the width. If the width is smaller, current is going to be smaller, which means leakage current is going to be smaller. So why we need to consider PMOS 2 times the NMOS? That is because PMOS, the main charge carriers are holes, NMOS charge carriers are electrons. And in a lot of traditional textbooks, the old ones, or at least the early technology nodes, PMOS or the hole mobilities, the carrier of PMOS, and the electron mobility, the carrier in NMOS, the ratio of their mobilities is 2:1. And since mobility has a direct effect on the resistance, therefore we take it as 2:1, which means since the mobility of PMOS is half the mobility of electrons, you need to make the PMOS device twice as wide so that you can get more charge carriers because the mobility is smaller. Therefore, we have 2:1. Hopefully that answers the question. So what about beta ratio in delay and how it contributes? So beta ratio is basically the ratio of P to N. So that has an effect on how or where the circuit switches. So we can talk about that maybe when you talk about characterization. Let's bring it up tomorrow. So aspect ratio, W upon L, I think is what you mean. So aspect ratio has an effect. So primarily what happens in digital gates is that people do not touch the L because they want to keep the L fixed. Only in analog circuits, sometimes they change the L. So in digital circuits, the aspect ratio is pretty much controlled by the width of the device and not the length. So any other question? So the aspect ratio is obviously, is it related to a logical effort or electrical effort? Yes, it is, because as seen here, the width of the device, as shown here, this 2 is representing the width, is going to control the capacitance. So therefore, it has an effect on the logical effort. And what is the electrical effort? It has an effect.
Sir, so while designing, should we have to decide the aspect ratio first, or should we have to decide the logical effort and the electrical effort, sir?
So logical effort and electrical effort does not depend on sizing. Okay. So once, let's say you have an inverter. So once you have an inverter and you have sized this inverter, this is your reference now. So once you have this as reference, what you're trying to do is you are trying to see if you can reduce the delay of the NAND gate or the NOR gate to be very close to the inverter. So once then you again fix the sizing. So once you've done that, for this condition, you know what the logical effort is. The logical effort is once you know what is your baseline sizing, you can know that I'm always going to have the delay of the rate of increase. Let's come back to these plots here. The rate of delay increase of a NAND gate is going to be 1.33 times more than the rate of delay increase for the inverter, because the slope is going to increase faster, right? So what it means is that if you want the same delay as an inverter, you need to reduce the load. So where is the delay of a NAND same as an inverter? So if you take this delay as an inverter, let's say some point on the y-axis for the inverter at this point, where is the delay equal for the NAND gate? I have to come to this point, which means if I want the delay of the NAND gate to come down, I have to now, to be equal to inverter, I have to drive a smaller load. So these become some of your trade-off. Now, if you cannot downsize it and you want to get the same delay as an inverter, the other option is I have to increase the size now. So it means I have to go up and I have to start going it this side, right?
Okay.
Basically, I have to bring it down, or I have to go on this side. So that becomes a trade-off. So that determines whether you want to size or not size.
So will that not affect the behavioral characteristics of any circuit, sir?
Affect what? Characteristics.
Behavioral characteristics, yeah.
Yeah, it'll not behavioral characteristics, but it'll affect the other parameters which are of interest. Like we talked about the constraints. It's going to cost you area. It's going to cost you power, dynamic power, and leakage power. So these become sometimes you have to pay penalty for this.
Okay, sir. Sir, in the coming in the session, can we expect one example taking all these parameters into consideration, sir? Taking the static power dissipation, dynamic power dissipation, and all that whatever we discussed today. So can we have one simulation? Will we get an opportunity to see that, sir?
Yeah, we will. I'll talk about power dissipation, dynamic, and leakage in the coming days and how it's characterized. Maybe we can talk about it at that time. Tomorrow it's going to be covered.
Okay, sir. So that we get to know that what trade-offs can be at least fit into it. So what
Sure.
trade-offs can be negotiable?
Sure. I think also what I want to highlight is, for example, let's take an example here. So you're making this again a very simple example. Let's take you're making some furniture. Let's say a table, right? A table needs a lot of different components, a lot of different things. Like you need wood, obviously. You need other things like nails. You need equipment. Let's assume that it's already there. So you need nails, you need glue, you need maybe some varnish, whatever, right? Now, let's take the nail. Nail is one of the smallest elements which make up the furniture. It's important, but it's very small. Now, let's say that I take a nail of some type that I already have, and I think that I can probably use another nail which is from a different company, which is double the cost. Double the cost.
Okay.
Now, just because I take a nail and I double the cost, does it mean that my cost of my furniture or my table has gone up by 2 times?
No, actually no.
Why?
Because the design still remains the same, the output still remains the same.
Yeah, but output may be same, but why do you think the cost is not increasing? I mean, I know you understand it, but I just want to know and see whether you understand it mathematically. Why do you think the cost is not increasing?
Because the output, whatever is expected, is still the same.
The output is the same.
Not
I'm talking
going
about
to
cost
change.
here. So why is the cost of the table not increasing?
Because
Yeah,
that
exactly. So
doesn't
as someone
matter.
said, no, it matters, but it matters very less. So if I break down the price, let's say bill of materials, there's a bill of material for each and every component, right?
Yes.
So let's say the bill of material adds up to some cost which is 1,000 rupees, and let's say each nail costs 50 paise, and I bought, let's say, 100 nails. Even if I buy 100 nails, it's not going to be a big percentage of the overall cost. Even if I double the cost of the nails, because one is I know that I can reuse this nail because I don't need to use all the 100 nails for the table, right? And even if I double the nails, for the number of nails that I've used, for those nails, even if I double the cost, because the percentage weightage or the cost of the nails is very small, doubling it doesn't matter. Maybe the nails which cost me 2 times more could be a better quality nail, could be a nail which is easy to nail inside, is much sharper, maybe it retains its shape, could be multiple reasons, right? So just because some gate is cost is increasing doesn't mean the design's cost is also increasing. It all depends on the trade-off and the weightage.
Okay, sir.
That's what I want to highlight maybe tomorrow. So we have to look at it from an overall system or a full design point of view. You can't look at it in isolation, right?
Sir. Yeah.
And that's how the trade-offs and optimization is usually done.
Right, sir. Right. For a beginner, it becomes a little difficult to even judge that what would be a nail in that design and what would be the real important part in that design. So that is where we get stuck, actually.
No, I understand. I think what I'm trying to say is that these sort of trade-offs are no different than the trade-offs which we usually make even in other parts of life, right?
Okay.
So you just have to look at it like, what is this, whether this piece makes up a big contribution or a small contribution. If the contribution is very small, even if I increase its overhead by 100%, it probably doesn't hurt me, right? And things like that. That is basically what is done in optimization and trade-offs.
Okay, sir. Yes. Yes. Yeah. Thank you, sir. Thank you.
Okay, I think we are at the end of the second break, and we basically are done for today. I think if there are no more questions, we'll just end it here. There's one more. Why do we prefer CMOS transmission gates over other gates? Is there any alternative for CMOS? So not CMOS transmission gates. CMOS transmission gates are basically another form of representing the switch. But CMOS transmission gates or other alternatives, you mean transmission gates or you mean just the gates? People don't use CMOS transmission gates to build logic because they are very slow. So transmission gates is used in very specific kind of circuits like multiplexers and so on. But otherwise, they are not very frequently. Multiplexers and other places like flip-flops. Maybe I'll talk about that tomorrow. I'll go through some flip-flop circuits. So that's where it's primarily used. But in other places like logic gates, it's more efficient to build them with regular CMOS transistors and not using transmission gates or pass gates.
So in the same complex design, can we use CMOS gates, pass transistor gate, as well as transmission gates, sir?
Yeah, usually when we talk about pass transistor, I think in the industry it's usually just transmission gate, because no one anymore uses just a single transistor, because as you may remember from your basics that it does not propagate the logic properly, right? So a full CMOS pass gate, which means a transmission gate, both NMOS, PMOS is used. Yes, it is used. It is used in places like when you're building a multiplexers, when you're building flip-flops or latches or clock gating elements. It's used. Maybe we'll talk about some of these flip-flops and other topologies, the circuits, and we'll cover that tomorrow.
Yes.
Okay, I think that we'll sort of end it here. We'll cover some of these questions, which certainly some of it will come up tomorrow again, when we talk about some of these flops and other circuits. We talk about some characterization and measurements for power and other things and optimization aspects. Let's discuss that in more detail tomorrow. And we'll just end it here today.
Okay, sir. Thank you, sir. Thanks to all the participants. Thank you.
Thanks. Bye.